we have a tool to compute the value set of any variable. So the value set is essentially a set of possible values that any particular variable could take on if the program were supplied different inputs. So this tool works by taking this intermediate language file, which was generated by Vine, and then computing a formula which relates all the inputs to the particular output we're interested in. And then it queries a decision procedure to solve actually this bounds. And in the case that's not feasible to solve exactly, we can solve it to arbitrary precision. So here's an example output. We see for this particular variable, here's the highest and lowest possible values that it could take on. And the influence, that is, how many bits of control does an attacker likely have over this variable, here is computed 15.9. So these are the tools we use to do trace-based vulnerability analysis. More information about all these tools, as well as some of the other tools we have for operating on traces, is available at our website. And now I'll let Charlie show how we actually use these tools to aid the analyst in analysis.
Thanks. So, so that was basically what. So, you know, I found about BitBlaze, and I knew the problem I wanted to solve, and then I had to figure out, you know, so I should say that basically the two problems I wanted to solve. One was figuring out which of a bunch of crashes are the exploitable ones, and then the second problem was, given one that looks exploitable, find the underlying bug. And so, you know, these are the tools that are available, and we work together, and you know, I would give suggestions, and they would try to implement them. And so I'm going to show you for some real, you know, examples here from fuzzing what happened. Okay, so let's start with Adobe Reader, a favorite target of mine. So I fuzzed it for 3 weeks. This is back in November, and I did 3 million test cases, found crashes at 100 different instruction pointers, of which Crash Wrangler, or not Crash Wrangler, Bang Exploitable said there were 33 unique crashes. And of those, it categorized them like this. So 4 were exploitable, 8 probably exploitable, 17 unknown, and 4 probably not exploitable. Okay, so there's a bunch of crashes, right? More than I want to look at. I don't even really want to look at all 4 exploitable ones, but I probably would do that. And so I mentioned Bang Exploitable, so let's talk about like what Bang Exploitable does and what we can do with BitBlaze, which is more powerful. So Bang Exploitable, the way it works is, you know, it doesn't have all this detailed tracing information. So it basically only looks at the basic block where the crash occurs and does a little slice on that. And as far as taint goes, it assumes everything's tainted because it's like, well, you know, it crashed, there must have been a problem. BitBlaze, on the other hand, has full taint information and full trace information. So it can slice beyond the basic block it's in to figure out where data came from, or at least you can have it do that. And furthermore, it knows exactly what's tainted and what isn't. And so from that, you can make more intelligent decisions about what is actually exploitable and what isn't. The drawback, of course, is that Bang Exploitable runs basically instantaneously, and BitBlaze doesn't. So BitBlaze, to record the actual trace, may take several hours. So I think of it as a tool like a fuzzer, where you turn it on, you go to bed, and you wake up in the morning, and you have all your traces. So it may take many hours. And running an actual slice, sometimes it happens really quick, a few seconds, but sometimes it may take, you know, an hour or two. So this is something, again, you really can't use sort of interactively a lot of times. You have to run it and then come back to it. But at least you don't have to think about it, right? It's better than reverse engineering in the classical sense. I mean, so here's another one about strengths and weaknesses. But the way I use it, so I think about using it as like I use a fuzzer, where, so, you know, fuzzers, they find bugs, but just as easily you could just, you know, read the binary, right? But the reason I don't do that is it's hard on my brain. But fuzzing is easy. I turn it on and I go away. And BitBlaze is the same way. So it takes longer clock time, but it actually saves you, you know, mental energy. Okay, so so it turns out, so the first problem that I wanted to solve was which ones are exploitable. So I have all this taint information, I have these crash dumps with taint, and you know, does that help me actually determine whether they're exploitable or not? The answer to that is sometimes. Maybe, you know, actually not as much as I thought. So I was like, well, if I have taint information and a crash dump, I should basically know what's going on. It turns out crashes, of course, are a little more complicated than you might imagine. So we'll see. One thing it is really good at is eliminating null pointer references. So of those 17 unknowns that Microsoft found, that Bang Exploitable found, you can, with BitBlaze, in just a matter of a minute, throw out 6 of them. So 6 of them for sure are not exploitable. So it does give crash reports with taint information. It's not so good at invalid reads. So why is that? Well, invalid reads, there's nothing exploitable about an invalid read, but what happens is sometimes then if you were to fix things up a little bit, it goes on a little bit and then maybe there's a write or something. But the problem is that's in the future. And you might be able to use Vine or something, but the tracing component at least doesn't tell you about the future. So there's some things it's good at, some things not so good at. Oh, that blue is bright. So this is basically another crash dump and what it looks like. So this is for Adobe Reader, and you can see things like, so it's actually, it's a read of what was an EAX, which happens to be, I can't really read, 0, right? So this is an example of null pointer dereference that Bang Exploitable said was unknown. But if you look at it, it's not, the 0 isn't tainted, so you can kind of, with a little more assurance, say, well, it's probably not exploitable. Here's another one. This is another invalid read on EDX. EDX here is some weird, crazy value, which maybe you think we made it that way. But actually, if you look, I don't see it, but it's not tainted. So it is a weird read, but it's not tainted. So again, probably not going to be exploitable, but I wouldn't say for sure. You can see some other things are tainted, but not EDX. Okay, so that was basically looking at trying to figure out which ones were exploitable. So with taint information and the crash reports, you can draw a little more conclusions, but still it's a lot of crashes, and there's a lot of them you don't really know about. But now moving on to say you do have some crashes you want to look at, and you want to figure out what the underlying causes of these crashes are. BitBlaze actually turns out to be really good at that. So the rest of the talk is basically looking at 4 examples of real crashes from Adobe Reader and other applications, OpenOffice as well, and seeing exactly how you would use the tools to figure out what the underlying problems are, or at least get started. So here's a crash in Adobe Reader. It's still in the most current version, but you'll see that it's not important. So this is a read from ECX, and if you look at ECX, it's 10, so it's near null. So if I was looking at this, I would probably say, it's probably a null pointer reference, but I would have sort of a nagging feeling in the back of my head, like, well, maybe it's not, right? So what happens if that 10 came from a wild read, right? And it could have been some other value, and then maybe it writes to that value, and it would have been exploitable, and I would have been really mad if I missed that. Or maybe it was, the 10 or the 0 or wherever came from an uninitialized value, right? So from some buffer that hadn't been initialized, and had I arranged things, I could have controlled that. Or maybe that 10 came from my input, right? I had this big file, maybe there was a 10 in there, and it used that, and I could have set to anything I want. So it's like, I'm pretty sure this thing's not exploitable. My gut tells me it's not, but I still, there's this nagging doubt. What BitBlaze can do is it can really quickly get rid of that doubt for you. Okay, so here's using BitBlaze for the first time on live TV. So trace reader, right? So I take my trace. This is the trace of the bad file, the one that crashed. And there's this header option that will tell you, like sort of meta information about it. And one of the things is it'll tell you how many instructions are there. And we're concerned for the crash on the very last instruction. So there's 27,000 instructions. So then I say, okay, now I know how many there are. Now let's just print out what the last instruction is. So I say, I want to see the first one is the last one. So it's the same thing we saw in WinDebug in the last slide. So it crashes on ECX. ECX is 10. ECX is not tainted. So, we already could have gotten that from a crash dump. It makes me feel like, well, at least it didn't come from my input, but it still could have been like an uninitialized variable or a wild read or something like that. So I'd like to know more about where this came from. And, where did it come from? Well, that's what the slicer is for. So let's slice on ECX and see where it came from. Okay, so here's using the slicer tool. This is what the command line looks like. I tell it where I'm at in the program. I'm at the last instruction, and I want to slice on ECX. And then it generates another trace, and then I print out that trace. So let's see what happened. Okay, well, ECX came from EBX, which came from a memory, or came from something plus 10, which was 0 plus 10, and then that got shifted around through various registers, and it started from a XOR of ESI and ESI. So I can know for sure now that the 0 or the 10, I had no control over that. It wasn't from memory. It wasn't a wild read. It wasn't an initialized variable. Just by running one command in BitBlaze, I know for sure this thing isn't exploitable. Where before I was, only kind of sure. So that's one thing that BitBlaze can do really quickly, and it's really good at. So what about comparing what happened in the good and the bad file where it crashed to the good file? So in the this is the same instruction again at the very top of the crash for the bad file. And then I use the alignment that BitBlaze gives you between the good file and the bad file to compare. So there's this script called align.pl. Only Noah writes Perl these days, but that's okay. So you give it the instruction counter where you're in one trace, and then it'll tell you what the corresponding instruction in the other trace is. So it says, oh, okay, for 27,000, you were some other 27,000 in the good file trace. And then I print out that instruction, and so at the same instruction in the good file, I can see that I had a valid value for ECX, which isn't surprising because it didn't crash. But I can see exactly what the value was. And in this way, you can compare the good file and the bad file pretty easily. And you can walk through and see exactly when things go wrong. And then likewise here, what I did was I sliced on that good value. In the good trace, I sliced on the good value. Where did the good value come from, right? Because it didn't happen in the bad file. So if I know where it got set, then I'll know why it didn't get set in the bad file. So this is, as a exploit developer guy, I'm done at this point. I already know it's not exploitable. But if I'm a developer, I want to know what happened. Why? I want to fix it. Well, if I care about no pointer references, which hopefully I do, although no one seems to. So here, if you do the slice again, then you'll see, oh, all of a sudden you can trace back the good value, and you can compare the slices from the good and the bad, and you can see exactly where the good value got set in the good trace. So, and then you can compare why that didn't happen in the bad trace. And then, so then you could see on the last one exactly the instruction where the good value was set for the good trace, and then you can look at the alignment and see exactly where that occurred. And it occurred in this big unaligned area. So in the good file case on the left, there were 5,300 instructions that were executed. In the bad file case on the right, there were only 6 for that same region. And so that's where things went wrong. So if you would have, you shouldn't have went down the branch with the 6 because it didn't set the value correctly. So this is the root cause of the bug here. All right, so then, when I flip the button, so then Noah's going to show, so I like the command line interface, but there's actually a GUI version of these tools as well that builds into IDAPRO and can help you. You just have to let it sit for a second. Okay, number 1, yeah. So if you like the GUI and you like IDAPRO, it's pretty cool. You can see the traces in them. So Noah, take it away.
Okay, so well, this window should be familiar to anyone in the security analysis field, right? This is IDAPRO, and what I've done here is I have a plugin running in the background, and using this plugin, I loaded the trace file, which we collected from Temu, for this particular sample that Charlie was talking about. And the first thing to notice is that the instructions are colored, right? So what do these colors mean? Well, so the blue code was executed in the trace, okay? That's all well and good. And we can go to any particular location in the code, and using the navigation commands, we can walk through the actual execution of the code. Okay, that's nice. We also have a taint list, which tells us all the instructions that operate on tainted data. So in this case, the very beginning of the trace started collecting when the program first read tainted input. So here we can jump directly to this location. It's reading some tainted value. And we have a register window which essentially prints out the contents of all the registers at any particular location in the trace. So here we can see this instruction is operating on memory, and hey, it's tainted because this address that it's operating on is tainted, and in particular the last byte is tainted. And we can see the byte was read here by this instruction. And so we can sort of walk through. Now we see we have a red colored instruction, which basically points out which instructions that we're looking at are tainted. And we continue to walk through. The green means that there's a data dependency. So the instruction operates on some data that was written by this one. And